Welcome to AI Research Radar, where we delve deep into the latest developments in artificial intelligence research. In today's episode, we explore a pivotal paper titled Large Language Models Must Be Taught to Know What They Don't Know by Sanyam Kapoor, Nate Gruver, and colleagues from renowned institutions like New York University, Abacus AI, and Cambridge University. This paper addresses a critical challenge in deploying large language models, LLMs, in high-stakes applications. The need for these models to reliably estimate their own uncertainty. Introduction. The paper begins with a compelling scenario. I have high cortisol but low ACTH on a dexamethasone suppression test. What should I do? Here, the importance of not only providing an answer but also conveying the confidence level associated with that answer is highlighted. This scenario underscores the potential dangers of acting on predictions made with unwarranted confidence. The core question the paper seeks to answer is whether LLMs can accurately represent uncertainty in their outputs, which is essential for their safe and reliable use in decision-making processes. Debate on uncertainty estimation. The research community is divided on whether LLMs can inherently estimate their uncertainty. Some argue that high-performance LLMs can provide calibrated uncertainties through prompting alone, while others claim that these models are often overconfident. This discrepancy is exacerbated by the varied linguistic structures in free-form text generation, making it challenging to achieve consistent uncertainty estimates. The paper introduces a dichotomy in uncertainty estimation methods, black box and white box approaches. Black box methods, which do not require model training, can be used with closed-source models like GPT-4. In contrast, white box methods involve fine-tuning model parameters on a calibration dataset, which is now more feasible with the availability of strong open-source models like Llama and Mistral. Fine-tuning for better uncertainty estimates. The authors argue that prompting alone is insufficient for good calibration. They propose a fine-tuning approach using a small dataset of graded examples, which significantly improves the accuracy of uncertainty estimates while maintaining computational efficiency. By fine-tuning the model through its features, they demonstrate that even 1,000 labeled examples can outperform baseline methods. Their method uses low-rank adaptation, LoRa, for fine-tuning, which is computationally tractable for large models. This approach not only improves the expected calibration error, ECE, but also enhances the area under the receiver operating characteristic curve, OROC, indicating better discrimination between correct and incorrect answers. Generalization of uncertainty estimates. The study explores the generalization capabilities of fine-tuned uncertainty estimates across different question types and tasks. The authors find that fine-tuning significantly improves the model's ability to generalize to new, unseen questions and tasks. They show that models can be used as general-purpose uncertainty estimators, capable of assessing not only their own uncertainties, but also those of other models. Impact on human-AI collaboration. To assess the practical impact of these improved uncertainty estimates, the authors conducted a user study. They found that providing users with reliable uncertainty estimates significantly enhanced the effectiveness of human-AI collaboration. Users were more likely to trust and act on the model's predictions when they were informed about the associated confidence levels, leading to better decision-making. Related work and contributions. The paper builds on a rich body of related work in uncertainty estimation and calibration in machine learning. It contrasts with prior studies that have focused primarily on black box methods or multiple-choice tasks. The authors introduce several innovations, such as regularization to maintain similar predictions to the base model and extensive ablations providing actionable insights. They also introduce a new open-ended evaluation setting, demonstrating fundamentally different trends compared to prior work on multiple-choice questions. Experimental setup. The authors conducted their experiments using a diverse set of benchmark datasets for training and evaluation. They used greedy decoding to generate answers and labeled them as correct or incorrect. For evaluation, they primarily used the MMLU dataset, expanding it with a new open-ended setting to test the model's ability to generate answers without predefined choices. Results and analysis. The results show that fine-tuning for uncertainty estimation leads to significant improvements in both ECE and OROC across multiple datasets and tasks. The authors also found that the amount of labeled data required for effective fine-tuning is relatively small, with even 1,000 labeled examples providing substantial benefits. They further examine the mechanisms enabling reliable uncertainty estimation, revealing that models can learn to predict the correctness of their own and other models' predictions. This generalization capability is attributed to the model's ability to recognize patterns in the training data that correlate with correctness, rather than relying solely on the content of individual answers. Discussion and future directions. The paper concludes with a discussion on the broader implications of their findings. The authors emphasize the importance of uncertainty estimation for making LLMs more interpretable and trustworthy. They suggest that future work should focus on developing single models capable of generating both answers and uncertainty estimates without switching between model weights. The authors also highlight potential applications of their methods beyond improving the safety and usefulness of LLMs. For instance, high-quality uncertainties can be used in active learning procedures to select data points based on predicted utility and model uncertainty, balancing the explore-exploit trade-off. Conclusion. In summary, this paper makes significant strides in addressing the challenge of uncertainty estimation in large language models. By demonstrating the effectiveness of fine-tuning with a small dataset, the authors provide a practical and scalable solution for improving the reliability of LLM predictions. Their findings have important implications for the safe and effective use of LLMs in high-stakes applications, ultimately contributing to the broader goal of making AI systems more trustworthy and interpretable. Thank you for joining us on AI Research Radar. Stay tuned for more insights into the latest advancements in artificial intelligence research.